Friends, let us pass on to the second chapter of our course in discrete mathematics. Here we discuss the ordered sets, languages and grammars, which are some of the basic concepts in theoretical computer science. Computability and formal languages. It is made clear in the first chapter that there are two methods to write a set, namely the list method and the rule method. Russell's paradox was introduced to describe the limitation of the rule method while defining a set. There are many other paradoxes also. Most of them are framed with an intention to strengthen our concepts in understanding various theories. The barber's paradox is one which is almost similar to that of Russell's. It is stated as follows. In a village, there is a barber. The barber shaves all those people and only those people who do not shave themselves. Then the question is, who will shave the barber? The possible answers are the barber shaves himself, which cannot be true as per the statement. Someone else shaves the barber, which also cannot be true as per the statement. Quite often, artificial situations are framed to make one think of finding the possible solutions to a problem. The solution will be obtained in systematic steps. We call such steps as a program. The problem may be simple or tough. Let us look at examples of certain programs. The preparation of tea to drink can be seen as a simple program. The different steps like take a pot, pour some water into it, put it on the stove, light the stove, put tea dust or leaves into it when water boils, add sugar if necessary, pour it into a clean glass, etc. are the different steps. Any change in the order of these actions may take you away from getting tea. As another example, just imagine the following situation. Suppose on your way to a place, the road diverts into two. Of these two roads, one leads you towards your destination and the other towards a dangerous place. Two soldiers guard these roads. Both of them know the places to where the roads lead. One of the soldiers tells only truth and the other tells only lie. Both of them look alike and you are not told who is the truth teller and who is the liar. In order to find the correct route, you are given chance to ask one and only one question to one and only one of these soldiers. With the question and the answer that you get, you have to identify the correct route. There is no one else to help you in this situation. The problem here is to find an appropriate question which you must ask and the decision that you would take on hearing the answer. You can ask the following question to any one of the two soldiers. If I ask the other soldier for the correct route to my destination, what would be his answer? On hearing his answer, you just have to skip the route shown by him and follow the other route. The following discussion explains the reason. Let us name the truth teller as T and the liar as L. Assume that you had asked the question to T. T knows the actual route, also T knows that L is a liar and would direct you towards danger. Thus, it is clear that the answer to your question told by T will definitely lead you to danger. So, you can take the other route to continue your journey. On the other hand, suppose you had asked the question to L. He will tell you only lie. He knows that the T will tell truth and so would direct you towards your destination. But because L tells only lies, he would tell the answer to your question as the exact opposite what T actually would tell. That means you will get the way leading to danger as the answer from L. Then also you would skip the route told to you and choose the other route. In either case, you will be able to identify the correct route. The story of the soldiers motivates us to work for obtaining suitable programs as a part of solving problems of different sort. For the task to be done with the help of a computer, we need programs. Since computers are powerful and versatile, one may feel that they are capable of solving any problem. But to what extent is this true? We have to accept the fact that there are tasks which no computer can perform. When put it differently, to prove the capability of a computer to perform a task, one must simply demonstrate manually or verbally the way the task may actually be performed. This leads to an important and thought-provoking concept in theoretical computer science known as the non-computability. Also, when we say a particular task is beyond the capability of all computers, it may be due to our ineptness as a user of the computers. But this possibility can be overruled as there are enough personnel to consult with. As a first step in getting a task done using a computer, we need a program and a suitable data. A computer program is composed of strings of letters, digits and special symbols. Any data also is made up in a similar way. In order to execute a program and analyze the data corresponding to a task, there must be another program, say the second program, which is already known to the computer and which would examine the first program and data for the task. But what program would examine the second program? Perhaps you may require a third program. But can you stop with the third program, or how far would you go along in this way? This discussion leads to an idea that there may be certain tasks which no computer can perform. Any program involves a set of statements or sentences. But how do we form such sentences and what are the rules? In this context, we introduce the concept of ordered sets. Ordered sets. The study of ordered sets become useful to write meaningful strings of letters, digits and symbols. There is a word of precaution about the term meaningful which will be discussed later. A set is always an unordered collection of objects. In practice, we often need ordered objects. For instance, consider the name of our country, India. It is an ordered set which can be written in detail as a 5-tuple INDIA. In this 5-tuple, the first element is I and the second element is a 4-tuple. In this 4-tuple, the first element is N and the second element is a 3-tuple or triple. In this triple, the first element is D and the second element is an ordered pair. In this ordered pair, the first element is I and the second element is singleton A. In a similar way, any English word is seen as an n-tuple where n is a suitable positive integer. This simple example illustrates the importance of ordered sets for developing languages. Consider a set consisting of alphabets, punctuation marks, blank spaces and other special symbols. A language is a collection of ordered sets on this set. The words form a set of all possible n tuples of elements from this set. If A denotes the set of alphabet, the set of all possible n tuples is usually denoted by A star. Then elements of A star are called words or strings. The English language that we use now has A equals set of all uppercase letters A to Z, lowercase letters A to Z, digits from 0 to 9 and the different punctuation marks. Any English book will be clearly a subset of A star. It is true that all the strings need not be meaningful. It is of course a grammar that makes meaningful strings for our need. If A is a finite set and if there is a well-framed grammar, a language over the set A can be seen as a subset of A star. In this case, A is called the basic set of the language. Example, taking A equals set A, B, C as the basic set, the following are examples of languages over the set A. L1 equals set A, AA, AB, AC, ABC, CAB. L2 equals set ABA, AAB, AA. L3 equals null set. L4 equals set A raised to I, C, B raised to J such that I greater than or equal to 1, J greater than or equal to 1. Since languages are sets, all the set operations can be applied on them. For a given set of alphabet, new languages can be obtained in this way by taking unions, intersections and differences. Phrase structure grammars. Any language is a set of strings formed using the alphabet and special characters or symbols. It is virtually impossible to list any language in the form of a set. So it is effectively described in terms of the rule by which the words and sentences are to be constructed. These type of rules are called grammar. There are different types of grammars developed to describe the different languages. Phrase structure grammar is one among them. A phrase structure grammar consists of 4 items: a set of terminals T, a set of non-terminals N, a set of productions or replacement rules P, and among all the non-terminals in N, there is a special non-terminal usually denoted by S that is referred to as the starting symbol. When we try to understand these terms in the context of English language, the terminals are symbols like articles, nouns of different types, verbs and adjectives which are used to frame sentences. The non-terminals are intermediate symbols used to describe the structure of the sentences. They are of the type sentences, noun phrases, noun, article, transitive verb phrase, etc. The productions are rules that specify how sentences can be framed in the language. It is described in the way a string is transformed into another string and finally into a meaningful sentence. A little more discussion is required to understand the meaning of the word meaningful. Sentence is considered as the starting symbol. After one sentence, the next sentence is framed. This process is continued till the message or idea to be conveyed is completed. In English, there is a well-defined grammar or rule for the formation of sentences. The process of producing meaningful sentences is referred to as productions. There will be different productions. They will use the terminals to form meaningful strings. Repeated application of productions provide us with a set of strings or sentences of the language. Example, consider the sentences. A dog finds a cat. Dog chases cat. The cat runs quickly. A simple idea is conveyed by the three sentences. Here we start with the starting symbol S. As we are looking forward to sentences, it can be assumed that initially we have an empty sentence. Sentence is noun phrase plus transitive verb phrase plus noun phrase, or sentence is noun phrase plus intransitive verb phrase. Noun phrase is article plus noun, or noun phrase is just a noun. Transitive verb is considered as transitive verb phrase. Intransitive verb phrase is intransitive verb plus adverb, or intransitive verb phrase is just an intransitive verb. In this example, we have A as an article, the as an article, dog as noun, cat as noun, finds as transitive verb, chases as transitive verb, runs as intransitive verb, quickly as adverb. It is clear that the above rules can generate the three simple sentences. With these rules, other sentences also may be formed. There are certain limitations to the phrase structure grammar. It need not be true that all sentences produced by a grammar will be acceptable. For instance, consider the following set of productions. Sentence is noun phrase plus transitive verb phrase plus noun phrase. Noun phrase is article plus noun. Transitive verb is transitive verb phrase. Monkey as noun. Banana as noun. A as article. Ate as transitive verb. Here, a monkey ate a banana and a banana ate a monkey both follow the prescribed grammar. So, they are valid sentences as far as the grammar is concerned. But only one of them is meaningful or sensible, and only that is acceptable to us. Thus, by a meaningful sentence, we mean only a sentence that is acceptable to us. It requires much more work to sort and select only the meaningful sentences and discard others from those generated using a grammar. Anyway, this is beyond the scope of our present discussion, and so we skip the details. It is very simple to identify the grammar when a language is given. Similarly, it is easy to develop the language when a grammar is prescribed. The following examples illustrate these. Example, let L equals set A A A A, A A B B, B B A A, B B B B be a language. This language has only a finite number of strings. The set of terminals can be taken as T equals set AB. The set of non-terminals is N equals set S. The set of productions can be taken as S gives A, S gives A B B, S gives B B A, S gives B B B B. Next example, consider the language L equals set A raised to I, B raised to 2I such that I greater than or equal to 1. Taking t equals set AB, n equals set S, where S is the starting symbol and S gives ASBB, S gives ABB as the productions, we can generate L. Next example, consider the language L equals set X such that X belongs to set AB star, the number of A's in X is a multiple of 3. Take T equals set AB as the set of terminals, N equals set SAB as the set of non-terminals, S being the starting symbol and the following as the set of productions. S gives BS, S gives B, S gives AA, A gives BA, A gives AB, B gives BB, B gives AS, B gives A. There are grammars of different types according to the way the productions are defined. If all the productions are in the form A gives A gives AB or A gives A gives BA, then the grammar is said to be of type 3. In the example 4.4, a grammar of this type is given. If in any production the left hand string is always a single non-terminal, then the grammar is said to be of type 2. The grammar in example 4.3 is of this type. If in every production of the form alpha gives beta, the length of beta is larger than or equal to the length of alpha, then the grammar is said to be of type 1. If no such restrictions are fixed, then the phrase structure grammar is said to be of type 0. The corresponding languages are classified into different types accordingly as the grammar. Let us summarize what we have looked so far. The important concept of non-computability was introduced in this module. The role of ordered sets in the formation of languages was highlighted. Phrase structure grammar and its use in describing languages were introduced. A brief mention about the different types of grammars was made. Try to answer the following questions. First, write a note on the use of ordered sets in the formation of languages. Next, let L1 equals set A raised to I B raised to j such that I greater than j greater than or equal to 1 and L2 equals set A raised to I B raised to j such that 1 less than or equal to I less than j be languages. Then show that L1 union L2 equals set A raised to I B raised to j such that I not equal to j, I j greater than or equal to 1. Next, let L1 equals set A raised to I B raised to j such that I j greater than or equal to 1 and L2 equals set A raised to I B raised to I such that I greater than or equal to 1 be languages. Then show that L1 difference L2 equals set A raised to I B raised to j such that I not equal to j, I j greater than or equal to 1. Next, construct a grammar for the language L equals set A raised to I B raised to j such that I j greater than or equal to 1, I not equal to j. Next, in what ways the grammars are classified into different types? The following books and sites are recommended as reference. Elements of Discrete Mathematics by C.L. Liu, Tata McGraw-Hill Publishing Company, 2nd edition. Introduction to Automata Theory, Languages and Computation by John Hopcroft and Jeffrey D. Ullman, Narosa Publishing Company. Applied Discrete Structures for Computer Science by Alan Dorr and Kenneth Lefaseur, Galgotia Publications Private Limited, New Delhi. The following websites also are recommended: www.mathoverflow.net, www.ideas.repec.org. Hope you have followed this session. We will meet again with the next chapter. Till then, goodbye.